All right, so we are in the last section that we cover in this class. Section 9.2, we're looking at another numerical method for solving first-order equations. In fact, it's a family of numerical methods. It's not just one method. And what we're going to see is that both Eulers' method and the improved Eulers' method are actually special cases of this method. So it generalizes all of the numerical methods that we have done so far, which have really only been two. So again, let's just remind ourselves of what Eulers' method is. Euler's method is a way of approximating a first-order IVP that takes this form, y prime equals f of xy, with an initial condition y of x naught equals y naught, and we're approximating some specific point on the solution curve of this first order, the solution of this first order equation, and what we're going to do here is basically take Euler's formula, which we know looks like yn plus 1 equals yn plus h times f of xn yn, and replace that slope function f of xn yn with a weighted average. Okay? And this weighted average is specifically a weighted average of slopes. The k1, k2, all the way through km that we're seeing in here represent slopes of the tangent lines to our solution curve at points within the interval of numbers between xn and xn plus 1. Because this specific, this instance of this recursive formula is taking us from the nth point to the n plus 1th point. Okay, so we're using several slopes within that one little interval where we make the jump from xn to xn plus 1 and doing a weighted average. Notice this is kind of like what we did with the improved Euler's method. We took two slopes within that interval and then averaged them. And we saw from the diagram, the graph that we showed in the previous section, why that kind of gave us a correction on our estimate. We call that a predictor-corrector method. And that's essentially what's happening here as well. The weighted average is going to end up giving us better results depending on how we go about that. So the K1 through Km, like we said, are specific slopes for a selection of points between xn and xn plus 1. And the weights, W1 through Wm, if you've worked with weighted averages before, are some set of positive numbers, or non-negative numbers, we should say, that sum to 1. That's what that requirement is necessary for it to be a weighted average. They can't just be any numbers. Okay? If we use a recursive formula that takes this form, the numerical method that's based on this is called a Runge-Kutta method. That's pronounced Runge. And the number m, so the number of terms that show up in this weighted average, determine what's called the order of that method. Now, right away, if we were to set m equal to 1, so if we're looking at a Runge-Kutta method of order 1, we would only have one term in here. And then if that's the case, W1 would have to be equal to 1 in order to satisfy this condition. And if we set the slope, K1, equal to f of xn yn, this would represent the slope of the tangent line where we're using the left endpoint of this interval as our x value, then this just reduces to Euler's method. Okay, because again, this weighted average in here is just going to become 1 times f of xn yn, or just f of xn yn times h, and you have the rest of this here. That's exactly what Euler's method is. So we say that Euler's method is what's called a first-order Runge-Kutta method. Okay, now we didn't have to choose this slope to be f of xn yn based on what we've seen up here. So far, the conditions allow us to choose K1 to be a slope to the slope of a tangent line to the solution curve at any x value between xn and xn plus 1. However, in order for this to qualify as a Runge-Kutta method, there is another condition that needs to be met. And that is that this weighted average here needs to agree with a Taylor polynomial of degree m, so where m matches the order of that method. And the reason for this is the same reason for why we were looking at Taylor methods back in section 9.1. Because according to Taylor's theorem, if you can expand a function using a Taylor polynomial, then this last term here is your error term. And by using that, we can put a specific upper bound on our error. That allows us to understand how accurate this method will be with a lot more certainty than if we didn't have this. So that's another necessary thing. We need to make sure that this weighted average right here agrees with a Taylor polynomial of degree m. In the case of our Eulers method, of this first order Runge-Kutta method, which we've already analyzed this, we're just going to look at it again. If we were to set a equal to xn here, where everywhere where an a appears, and x equal to xn plus 1, then x minus a is the difference between xn plus 1 and xn, but that's how we define our step size, and so xn plus 1 could also be written as xn plus h. If we make all the necessary substitutions up here, this polynomial reduces to this. Okay. Now, in the case where we're looking at a Taylor polynomial of degree 1, like we are in the case of Euler's method, degree 1 would only give us up to this first degree term right here, and then we would have plus our remainder term. But the Taylor polynomial itself would simply look like y of x plus n, or sorry, y of xn plus hy prime of xn. Y of xn we simply call yn if we assume that yn is exactly equal to the correct value, but from plugging in xn into our solution. And remember, we made that assumption in error analysis when we talked about local truncation error in the previous section. So under that assumption, we called this yn. And then y prime of xn is the slope to our solution curve at xn. But that's exactly what f of xn yn does. So that y prime of xn can be replaced by an f of xn yn, and notice the whole thing just reduces to Euler's method, which means the remainder term is exactly the error that we would obtain using Euler's method to do one step, one iteration in approximating a point on our solution curve. Okay, so we've kind of talked about that already in section 9.1 when we looked at error analysis. That's just kind of a recap of that. But now, let's move from a first order Runge-Kutta method to a second order Runge-Kutta method. Now, for a second order Runge-Kutta method, we would be looking at a recursive formula that takes this form. Yn plus 1 equals yn plus h times a weighted average containing 2 terms, because that's the order of this method. Now, again, the conditions that are required of a Runge-Kutta method leave some flexibility as far as how we choose k1 and k2 and our weights, just so long as the weights add up to 1 and the slopes are given in that interval from xn to xn plus 1. However, we're going to place some additional we're going to be a little bit more descriptive about what K1 and K2 need to look like in our case. And we're not going to walk through kind of the argument as to why we're choosing it this way. That's better handled in kind of a numerical analysis class. But what we're really doing is we're selecting our slopes K1 and K2 in such a way that they lead to a system of equations that will naturally agree with that Taylor polynomial. It's a longer explanation than we're really going to want to go into here. But K1, if you just take a look at K1, it's equal to f of xn yn. So the slope K1 in this case is exactly the same slope we would use in Euler's method. It's the slope to our solution curve at the left end point of that interval xn plus 1. K2, the second slope, has to be a different slope than K1. And if you notice, we have xn plus alpha h, and that's the x value that's being chosen here. And that alpha is a parameter. You can choose different values for that alpha. However, we would need this slope k2 to be within within that interval from xn to xn plus 1. And so if alpha was equal to 1, then this number here becomes xn plus h, which is the same thing as xn plus 1. That's as far to the right as we're allowed to go in that interval. So what that tells me is that alpha needs to be greater than 0, but less than or equal to 1. So it's somewhere between 0 and 1, possibly equal to 1. And then yn is equal to beta hk1. And if we remove that beta right there, or if we set beta equal to 1, if you think about that, this is the linear approximation for y of xn plus 1, because what we're doing is we're using hk1, which is going to give us, if you remember talking about differentials back in Calculus 1, it would give us that linear approximation. Beta, just like with alpha, is a parameter, and this allows us to kind of shift where that linear approximation is and correct it. And if that's, I know that's probably not making a whole lot of sense because I'm not going deeply into that discussion, but what's really important for us to understand here is that we're selecting K2 in such a way that we're still plugging a point into our slope function, and this will give us some point that's valid to choose, and we'll also agree with the Taylor polynomial of degree 2, which we need that to do. Okay, so these are going to be the choices for K1 and K2, and that means that we need to solve for some of these parameters here. We need to know what alpha and beta are equal to, and we also need to know what the weights W1 and W2 are equal to. And again, we're not going through the argument here because it's a little bit beyond the scope of what we're trying to accomplish, but you can take my word for it. It can be shown that if we want this to agree with a Taylor polynomial of degree 2, then for one thing, W1 plus W2 has to equal 1. That's required just because we're talking about a weighted average, and we talked about that condition already. However, we can also show that W2 times alpha would have to equal 1/2, and W2 times beta would have to equal 1/2. These requirements will allow this to agree with a Taylor polynomial of degree 2. Now notice that this is a system of 3 equations, 1, 2, 3, in 4 unknowns, W1, W2, alpha, and beta. The implication there is that we actually have an infinite number of solutions for those 4 parameters. And if you notice, W2 appears in all 3 of these equations. So what we can do is isolate W1 here, isolate alpha here, isolate beta here, and make those 3 parameters, W1, alpha, and beta, functions of W2. So basically what that means is that W2 is allowed to be any number that you want it to be as long as it's not equal to 0, and we'll see why in a moment. Well, actually, you can see why right away. If W2 is equal to 0, then neither of these will ever equal 1/2. But as long as you choose W2 to be some non-zero positive number that's less than 1, less than or equal to 1, then you can use that to determine W1, alpha, and beta. So on this next page here, we have done exactly that. We've written all of those other 3 parameters as functions of W2. Okay? So what that means is that if we're using these conditions to determine what a Runge-Kutta method of order 2 looks like, there are infinitely many such methods. Because again, we have infinitely many valid choices of W2 to use here. However, depending on how we select those points, we may obtain a familiar method that we have already looked at. So to show that, let's select W2 to equal 1/2. Well, then W1 is equal to 1 minus 1/2, which is 1/2. 1 over 2 times 1/2 is 1 over 1. And that would be the same thing in both of these cases. Alpha and beta would both be equal to 1 in that case. What does that look like in our Runge-Kutta method? Well, go back to your recursive formula here. If W1 and W2 are both equal to 1/2, which is what we just determined, then that becomes a 1/2 that both of these terms have in common, and I can factor that out and write that as h over 2. Giving me this, yn plus 1 equals yn plus h over 2 times k1 plus k2. And then on top of that, the way that we defined K1 and K2 in these two equations here, K1 we already said is f of xn yn, so there's no place to input any of those parameters here. But if we plug in 1 for alpha and beta, which is what we solved for, then we get xn plus h plus yn plus h k1. That's this. But this is the improved Eulers method that we talked about in the previous section. So that shows that the improved Eulers method is a Runge-Kutta method of degree 2. Now, I didn't write this in this notes, but it's in your book, and I want to mention this. Because we've made a connection between the order of a Runge-Kutta method, so let's go back to this first order one, and a Taylor polynomial that has the same degree, right? So the Runge-Kutta method of order 1 will correspond to a Taylor polynomial of degree 1, which means its remainder term will, which represents its error, will have an order of h squared. Okay, and we talked about that back when we did error analysis. What this shows is that the higher the order of your Runge-Kutta method, the higher the order of your error term. And when we talked about error analysis, we said that the higher the order of your error term, the more accurate your method is. And so that implies that if we want good accuracy using this method with approximating solutions to these IVPs, then we should go with a higher order Runge-Kutta method. But in practice, you never see anybody using a Runge-Kutta method of order 10 or order 100 or order 1,000 or anything like that. And the reason for that is every time you increase the order of a Runge-Kutta method, the calculations involved become more complicated. There become more steps. We already saw that going from an order 1 method, which was Euler's method here, to an order 2 method, which involved calculating two slopes and then putting them into a slightly more complex recursive formula. So there's a trade-off that occurs here, and it's a trade-off that's always looked at when you're talking about numerical methods in general. It's the trade-off between accuracy and cost. And remember, cost is the number of steps, the number of computations that have to take place for that algorithm to be used. And so somewhere there's going to be some kind of a balance. And believe it or not, it doesn't take that much time to get to that balance. The Runge-Kutta method that's used the most often in practice is of order 4. We've talked about order 1 and order 2. There are Runge-Kutta methods of order 3. We could easily talk about those. But because order 4 is what's used in practice, we're going to skip to order 4. Okay? So in the case of an order 4 method, we're looking again at this recursive formula where this thing in parentheses here is a weighted average containing 4 terms now. And again, we're not going to walk through a detailed argument as to why these slopes look the way they do, but we're using the same intuition that would have been used in the order 2 case. K1, our first slope, is the slope of our solution curve at the left end point of that interval, xn plus 1. So this first slope is like what we would be using in Euler's method. The second slope resembles what we used in the order 2 case where we had alpha and beta, but now I'm calling it alpha 1 and beta 1. And then in the third and fourth slopes, if you notice, the x value looks pretty similar in each case. Okay, and generally what would happen is A1, A2, and A3 would be in increasing order, because what that does is that selects x values that continue moving from left to right in that interval that we're choosing from. And notice every time we do this, our y value picks up an additional term. So here we had yn to start with. Now we have yn plus b1 hk1. And then we end up with yn plus b2 hk1 plus b3 hk2. We never reuse any of the alphas or betas, but we are reusing the slopes. K1s, K2s, and K3 is only showing up once here. So again, not going through a detailed argument as to why it looks the way that it does. We probably could, but it's more time consuming than I think is worth our time right now. The point here, though, is to look at how many parameters there are. Okay, we have alpha 1 through alpha 3. We have beta 1 through beta 6. So far, that's 9 parameters. And then we have W1 through W4. That's 13 parameters. Okay? In order to get this to agree with a Taylor polynomial of degree 4, it turns out that we'll end up with 11 equations this time. Remember, in the case of order 2, we had 3 equations. Order 4 is going to yield 11 equations in 13 unknowns. Now, because there are more unknowns than there are equations, again, that implies that we have infinitely many solutions. But solving a system of that size by hand is impractical. Obviously, it can be done, but there's no way we're going to spend all of the time that it would take to go through that. It's not worth the time, okay? But obviously, it can be done. And because there are infinitely many solutions, that implies, once again, there's infinitely many Runge-Kutta methods of order 4. But there's one particular choice of those parameters that ends up being the one that's used pretty much every single time we use Runge-Kutta method of order 4. And that would yield the following set of equations. So what that would do, we would select W1 and W4 to each equal 1/6. W2 and W3 would each equal 1/3. That sums to 1, like the weights are supposed to. And I could factor a 1/6 out of that. That gets me this. Yn plus h over 6, k1 plus 2k2 plus 2k3 plus k4. So that's just how that simplifies down. K1, nothing changes, right? There was no parameters in there, so it's still f of xn plus, or xn yn, no plus. Alpha 1 and beta 1 would both be equal to 1/2. Alpha 2 and beta 3 would each equal 1/2. Or sorry, yeah, alpha 1 and beta 1 are 1/2. Alpha 2 and beta 3 are equal to 1/2. Beta 2, this guy, is going to equal 0. So that ends up allowing us to lose that one term right there. Then we have alpha, I talked about, yeah, alpha 2 and beta 3 we talked about. Though I'm getting confused which ones we've talked about. No, yeah, I think we talked about that one already. And then down here, alpha 3 is going to equal 1, and beta 6 is going to equal 1, beta 4 and beta 5 equals 0. Okay, so basically, this method is one of the reasons we use these selection of values for those parameters, is there's a few that become zeros, and the computational work that's going on in these steps here is reduced a little bit, okay? Now, because this method is used far more often than other choices of those parameters for an order 4 method, we frequently just refer to this as the Runge-Kutta method of order 4. And more often than not, we just simply call it RK4. In fact, this method is used far more often for numerical purposes than Eulers' method or the improved Eulers' method. This is kind of the numerical method of choice in most applications where it applies. And so oftentimes you'll even hear somebody say, use Runge-Kutta, or use the Runge-Kutta method, and usually what they're referring to is RK4. So let's do an example before we wrap things up. Now this example is the one from your book. I'm using it because I wanted to use the chart that they had that did the comparison. I like this because we can line up all of our methods and see how they compare. So in this one, we are using the Runge-Kutta method of order 4, so RK4, and our step size we're choosing to be h equals 0.1. I think in the book they also do 0.05. You can look at that in the book if you'd like. I just want to look at this particular step size. And we're approximating y of 1 plus 1.5, where the IVP that we're looking at is y prime equals 2xy, and y of 1 equals 1. Notice, for one thing, that this is a very, very straightforward separable equation to solve, which means we can get an exact solution for this. It turns out this IVP has an exact solution of y equals e to the x squared minus 1. It's a good exercise to do that yourself, just to go back and practice, solving separable equations. But the benefit of that is that we can not only compare the approximations that we get from our three methods that we've talked about, Euler, improved Euler, and RK4, we can also compare those values to the actual value that they're supposed to be approximating. And we see that the approximations in RK4 are exceptionally good. So what does it look like to do RK4? When we do it by hand, it's kind of a beast. It's a lot of manual calculation. So K1, remember that would be, we're starting at 1 for x naught. So K1 of x naught, y naught is the same thing as K1 of, or f of 1, 1, which is 2 times 1 times 1, or 2. K2, and again, remember, these are the formulas that we're using right here to evaluate these. Xn plus 1/2 h, yn plus 1/2 h K1. So in this case, x naught, again, is equal to 1. Our step size h is equal to 0.1. So this would be equal to 1 plus 1/2 times 0.1. And this is going to be equal to 1 plus 1/2, 0.12. We're plugging that into our function f, which is equal to 2 times this times this. So 2 times that first value times that second value. That goes into a calculator. We get 2.31. And then we, evaluate K3 and K4, again, using those formulas. So you set this up in each case. Notice that the steps will look very, very similar. So if I look at K2 here and how it compares to K3 here, the only difference from K2 to K3 is that I'm using the slope that was found in the previous step. So I found a 2 here, that shows up here. In K2, I found that to equal 2.31, that shows up here, okay? Then we plug that in and we get this guy. K4 also looks similar, but K4 doesn't have the 1/2s here and here. So we're still using the slope from the previous step here, and we get 2.715361, okay? Now, the point of finding K1 through K4 was so that we had the slopes that we needed to plug into that weighted average in the recursive formula, which remember was K1 plus 2K2 plus 2K3 plus K4. These are K1 through K4 right here, so that all gets plugged in. We multiply that to our step size over 6, so 0.1 over 6, plus the y naught, which in our case was 1. That's from our initial condition. All of that gets plugged into a calculator. We get 1.233674335. That is only one iteration of RK4. So you can see that doing this by hand is not really practical. In practice, this is obviously done using computers. But even then, if you use RK4 for the kinds of approximations you'd be doing in practice, usually you're doing more than 5 iterations. So notice here, to get from 1 to 1.5 using a step size of 0.1, that's a total of 5 iterations that we would need to do. It's a lot to do manually. It's no problem for a computer. But in practice, you might have to do a couple hundred, couple thousand maybe iterations by using a very small step size to get that approximation. And by decreasing the step size, thus increasing the number of steps, you're putting a heavier cost on the algorithm for the software, the computer, to deal with. And so it can still be a costly algorithm depending on the size of your step size. But all that said, if we did all 5 steps, which we're not going to show all the work for here, we would end up with these values for RK4. Now notice, if we compare the values in this table, here's Euler's method, here's the improved Euler's method, here's RK4, and then here's the actual values using what we found to be the solution for this IVP. And comparing them, notice Euler's method is not terribly accurate, but we already knew that to be the case. From what we saw in section 9.1, improved Euler's method really does improve it by a lot. That gave us 3.4509 compared to a true value of 3.4904. So it gave us up to 1 decimal place of accuracy here. But RK4 does a significantly better job. 3.4902 compared to the actual value of 3.4904. And again, the reason we're getting these successively better approximations is not coincidence. It's because each of these is a Runge-Kutta method, but the order is increasing for each method. This is an order 1 method, order 2 method, order 4 method. So again, we're seeing numerically with this one example that the higher the order of the Runge-Kutta method, the more accurate your results will be. Okay? We could do a little error analysis with this as well, but I'm not really concerned with going that far with it. This is meant to be a very, very brief introduction to this. If you wanted to study these numerical methods more, that's what you would do when you're taking a numerical analysis class. You would dig much deeper into these. Okay? That's going to wrap things up for this chapter.